Welcome to Buffered Solutions. Today what we're going to do is we're going to talk about buffer solutions and how they're made and what they actually do. So to start out with, we have to start talking about conjugate pairs. And if you look at what we have here, we have sulfuric acid reacting with sodium hydroxide to produce sodium hydrogen sulfate and also water. If you look at the difference between, say, the sulfuric acid and the sodium hydrogen sulfate, what you have is this particular one has one more hydrogen than the sodium hydrogen sulfate. So this becomes our acid in that pair, and this becomes our base. Now, if you notice, what we end up with when we have this base from the acid is we end up with actually a basic salt. And that's going to be important as we go forward. So these two are conjugates of one another. Looking at the sodium hydroxide and the water, what's happening is if you just took a look at the OH piece of this, the OH becomes H2O by adding one hydrogen, and this guy is our acid. And our sodium hydroxide is our base. Okay, that's pretty straightforward with that type of reaction. But as we look down at this particular reaction, we have ammonia reacting with hydrochloric acid to produce ammonium chloride. And what we're going to look at here is the ammonia converting into NH4, and so this actually is increasing by one hydrogen, and so the NH4 is the acid. And so really this is the conjugate salt of ammonia, and this is the base. And we're going to kind of leave alone the hydrochloric acid, because really what we're doing here is losing one hydrogen to become chloride ion, and those would be the conjugates also. So the salt in this case for this base is the ammonium, and we're going to look at those as we go forward. Okay, so looking at salts, if we look right at the ammonium chloride was created from the ammonia plus hydrochloric acid. Now, ammonia is a weak base, and hydrochloric acid is a strong acid. And so when you get a salt that's created by a weak base and a strong acid, you actually get a slightly acidic salt. Okay, and the same thing, well, as we go forward, sodium chloride is created from sodium hydroxide and hydrochloric acid, which both substances are strong, so therefore when they create a salt that is neutral. If you have a strong base, such as sodium hydroxide, reacting with a weak acid, hydrofluoric acid, you actually get a slightly basic salt. Okay, so we're going to use these salts as we go forward, because we're going to create a equilibrium system. We're going to add a salt or a conjugate of an acid or a base to create this buffered solution. And so as we go forward, the definition of a buffered solution says here, an acid buffered solution is we add a weak acid and its conjugate salt. And so in this particular case, we have this compound HCNO, and we have the conjugate salt, sodium, and then the CNO. And so if you think about equilibrium, what's going to happen is typically in an acid-base equilibrium, we're having this dissociation where we have an H plus being produced, and then we have this CNO minus being produced. And in that process, what's happening is we have this dissociation between these two things. Sorry about the mess. What we're going to do is we're going to add this sodium compound. It's going to dissociate, and what it's going to do is it's going to give us some of that anion that is being released. And so what happens is we're actually increasing the amount of this substance. And if you remember from equilibrium, if we add something that is already in the reaction, it's going to push away from that side. And so by adding this, it's going to need to produce some more reactant. But in the process of doing that, it pulls some of this hydrogen with it. And so what we're essentially doing in a buffered solution is we're storing up those hydrogens for later on. And so what we're going to do is we're going to look at a general equilibrium situation, then we're going to look at a buffered equilibrium situation. So if we look at this next screen, This is the typical equilibrium that we've done for acids and bases. We start out with an acid, it dissociates into H plus and A minus. Initially, so we're going to use ice. Initially, let's say it's 1 molar. Both of these are 0, and they're both going to increase by some quantity. And so we don't know what that is, so we'll call it X. And it's a 1 to 1 to 1 ratio, so it's plus X minus X. So we take the initial concentration minus the change, 1 minus X, and we get X and X, and we put it in the equilibrium expression. Now, I used the Ka for acetic acid. Just acetic acid is a nice one to use in this particular case. What I did is I took this equation and I actually graphed it. And so if we look at the graph here, and if I pull this back down so we can see the graph, we will see that in this particular graph, what I did is in F1 I put in the K value, and F2 I put in the ratio, and then I zoomed in a bunch so that we could get nice and close to these intersection points, because if you think 1.8 times 10 to the minus fifth, that's nearly 0. And so once I zoomed in a little bit, I did a graph, or I found the intersections, and you'll notice I ended up with an intersection here of 0.004. Now, that's my X value, and if you remember back to what we were doing with X, X is simply the H plus concentration. So a question like this would ask something, what is the pH of the reaction? Well, once I found X, all I need to do is take minus the log of that X value, and I come up with 2.40 basically. So that's what we'd do with a typical equilibrium. Now, when we go into a buffered situation, what we're going to do is we're going to set up the same scenario, but initially we have this conjugate base in there, and which is adding some of this A minus initially. And so what we're going to do is we set it up like we did before. We have the 1 molar HA, we have 0 H plus at the beginning, but we have this other conjugate that we added, so we have to put that in there, that 0.5, which is going to play with the equilibrium. So then we do the same type of setup. We get 0.5 plus X as opposed to just plus X. But hydrogen is still X. We go down, set up our equilibrium expression, and then again I graphed that and I found an intersection point. Again, I zoomed in on this so it looks really good. The Ka is listed in F1 and the ratio is in F2. Found the intersection. Here is now this is now the X value. Again, X value is the H plus concentration. So using that X plus concentration, now I can figure out the pH. pH of this solution now is 4.4. So we've actually increased the hydronium concentration by every pH is a move of 10, so we've increased by basically 2. So we've increased by 100 times. And so just by adding in some of that conjugate base, it shifts the equilibrium. Now, an easy way to do equilibriums is, or I'm sorry, to get pHs from a Ka and concentrations is this thing called the Henderson Hasselbalch equation. And basically what it says is that the pH of a solution is equal to the pKa, and we really haven't talked about this guy yet, but remember that pH is minus the log of the H plus, so pKa must be minus the log of the Ka. And then we take plus the log of the ratio of the conjugate. Okay, so this little guy up there, that little guy on top is actually the conjugate salt. So this is the concentration of the conjugate, and this is the concentration of the acid. And so what we do is we set this ratio up, and then we solve this for a pH, or we might even solve this for this ratio, but what we have to do is we're not going to know one piece of this equation. So what I did is I said, well, what is the pH of a solution created from 0.2 molar acetic acid and 0.1 molar sodium acetate? And so we set up the ratio, we put in the Ka, and what we get is the pKa is 4.7 minus the log of that number. And then what we do is finally put this all together, and we get it all set up, and we're done.